Welcome to the Explainer. Today we're going to dive into the world of fluid power. And really, it's a tale of two systems, almost like two very different siblings, hydraulics and pneumatics.
Okay, so have you ever noticed that some big, powerful machines have this deep hum, right? But others have this sharp hiss? Well, that sound, it's not just random noise. It's actually a massive clue about how these things work on the inside. And today, we're going to figure out exactly what's going on.
All right, before we get into what makes them different, we've got to understand what makes them the same. So let's meet the family, so to speak. Both hydraulics and pneumatics, they play by the same set of rules. Three core principles that are like the family rules of all fluid power.
Okay, rule number 1, the valve position. Think of a valve as a traffic cop for the fluid. You flip its position one way, and it tells the actuator, the part that actually does the work, like a cylinder, to extend. Flip it the other way, and it retracts. Simple as that. It's all about direction.
Next up, pressure. This one's all about force. You might remember this from physics class. It's basically Pascal's law. The more pressure you cram into the system and push against a surface, the more oomph, the more force you're going to get out the other end.
And the last family rule, it's flow rate. And that determines speed. It's pretty intuitive, right? The faster you pump the fluid into that actuator, the faster it's going to move. So just to be super clear, direction, force, and speed. These three rules apply to both hydraulics and pneumatics. They're the common ground.
All right, now for the fun part. Let's get to the big family drama. The one key thing that makes these two systems totally different from each other. And you know what it is? It all comes down to the kind of fluid they use. And here it is, the absolute core difference. Hydraulics use liquids, like oil, which are incompressible. You can't really squeeze them. Pneumatics, on the other hand, use gases, like air, which are very compressible. You can totally squeeze air into a smaller space. And this one little detail, honestly, it changes everything about how they behave.
So to really get this, let's use an analogy. Think of a hydraulic system, like a school bus that's already completely packed with kids. The kids are the liquid. They're incompressible, right? You can't squish them. So when one more kid shoves their way onto the back of the bus, what has to happen? Someone immediately has to get pushed off the front. The flow is direct, it's instant, it's totally rigid and predictable. One in, one out. Now, let's think about pneumatics. This is like starting with an empty bus and trying to stuff it full of balloons. The balloons are the gas, they're compressible. You can just keep shoving more and more of them in there. They'll squish down, get smaller. You can pack a ton in. They compress and compress until the bus is totally full, and then whoosh! They can all burst out at once. It's not a steady one-in, one-out flow. It's a surge, a totally different feel.
Okay, so this whole kids on a bus versus balloons on a bus thing, it isn't just a silly analogy. It has massive, real-world consequences for how these systems act under pressure. Let's see what that ripple effect looks like.
So let's put this to the test. Imagine we tell a cylinder to extend, to move forward. But oh no, there's something in the way. It's blocked. What happens now? How do our two very different systems react to this problem?
Well, the hydraulic system, it just stops, dead in its tracks. It's like hitting a brick wall. That oil is incompressible, remember? Those kids are already packed in tight. There's nowhere for the fluid to go, so the whole system just goes completely rigid. It's locked.
But the pneumatic cylinder? Aha, that's a different story. It doesn't just stop. It keeps trying to move. It has this spongy feeling, a bit of give. Why? Because the air inside, our balloons, can compress. It squishes down, storing up all that energy, building up pressure, just like you're compressing a giant spring.
And right there, that's the whole ballgame. The compressible nature of air makes the pneumatic cylinder behave in a fundamentally different way. One system is rigid. It's perfect for things that need immense unyielding force, like lifting something heavy and holding it steady. The other system is spongy. It acts more like a shock absorber. It's perfect for jobs that need a little bit of give, a little bit of bounce.
Okay, so now that we get the whole rigid versus spongy difference, the big question is, where do you actually use these things? When would you pick one over the other? Let's do a little head-to-head showdown.
This chart here really lays it all out. Look at the fluid. Oil is messy, it's heavy, it's expensive. Air, it's literally everywhere, it's clean, and it's free. For power, hydraulics is your go-to for the really heavy-duty stuff. Think construction equipment. Pneumatics is more for light to medium-duty jobs. And that means the components are different too. Hydraulic parts are big, heavy, and cost more. Pneumatic parts are smaller, lighter, and cheaper. So you see hydraulics in big machinery, but you see pneumatics all over the place in things like food processing or medical devices, anywhere you need precision, and you absolutely can't have a messy oil leak.
And this brings us right back to where we started, that sound. With hydraulics, the expensive oil has to be pumped back into a tank to be used again. But with pneumatics, well, it's just air. Who cares? You don't need to collect it. The system just vents the used air straight into the atmosphere. And that is the source of that classic, unmistakable hiss.
Now, it goes without saying, but with all this power comes some pretty serious responsibility. Both of these systems are incredibly useful, but we gotta talk about safety, because they can be really dangerous if you don't respect them.
First off, the pressure hazards. The fluid, whether it's oil or air, is under an insane amount of pressure. If a hose bursts, that's a huge problem. And don't ever underestimate compressed air. People get complacent, but high-pressure air can literally cause blindness, deafness, or even inject air into your bloodstream. And if it escapes, it can kick up a storm of sharp, dirty debris. It's no joke. Then you've got the mechanical dangers. An unsecured high-pressure hose can whip around like an angry snake. Seriously, it's terrifying. And the actuators themselves, they move with enough force to punch right through metal. You have to be incredibly aware of all the pinch points and anywhere these things can travel.
And last but not least, stored energy. This is a big one. Just because you turn the machine off doesn't mean it's safe. A lifted object is storing gravitational potential energy. Components like accumulators or even just the compressed air in a pneumatic system are storing pressure. You always have to block everything out and safely relieve all the pressure before you even think about doing maintenance.
So, the next time you're out and about and you hear that hiss, what kind of power are you really listening to? Now you know. It's not just a noise anymore, is it? It's the sound signature of a compressible, clean, and incredibly versatile system hard at work. Thanks for tuning in.